Okay. Hello, everyone. My name is Jacopo Poli, and I'm the lead of machine learning at LightOn. This is the 16th edition of the LightOn AI Meetup. And we have Manuela Girotti with us, who is assistant professor at St. Mary's University and unspecified affiliation at Mila, apparently. She's going to be talking about convergence analysis and implicit regularization of feedback alignment for deep linear networks. And if I understand correctly, this was something that came out of the school in Les Houches.
Indeed, yeah.
A lot of people we know actually attended, and I think
yeah.
Ruben, who is in the public, attended that too. So it's going to be really interesting to see what you have to present. And yeah, you can start right ahead with the presentation. Thanks a lot for accepting the invite.
Yeah. So thank you, Jacopo, and thank you everybody for coming here. I know that it's 6 p.m. over there, so it's very late, and so I'll definitely try to keep it short so that we keep it short and sweet. And yes, so this work on feedback alignment. So my unknown affiliation with Mila is because I was a postdoc at Mila until a few months ago, and so that's why we're trying to continue this collaboration. And definitely this whole idea of deep feedback alignment came up in the summer school in Les Houches last year. So I just wanted to give a big shout out to Florent, because thanks to him and Lenka, I actually managed to get in touch with this work, and I see Ruben there, and he also worked on this. So I actually see a lot of experts in the audience. So I hope this talk will be interesting to them. So this work is practically just a theoretical work. So we did some experiments, but our goal was really to understand and to give some convergence guarantees of these for these algorithms, and then analyze a little bit of some of its properties, which is what is over on the top part over here. So you can see that we are working on. Oh, sorry, seems like. Oh, I'm really sorry. Okay, just 1 second. My pen just lost connection. I'm just gonna disconnect for a second. Really sorry.
No problem.
It's connected now. Okay. Yeah, should be back. Okay, perfect. So outline of the talk is just some convergence analysis about the feedback alignment, and this what we call implicit regularization or anti-regularization, which is some behavior that the algorithms displays depending on the initialization. So this was something that we found while we were studying this algorithm. And so I'm going to start with some introduction, which of course all of you know. So I'm going to go quickly through the introduction. So the idea is that we consider a neural network, and in this case it's like one hidden layer neural network, and then A is the pre-activation element, and then we apply some nonlinearity that we call sigma, and then we apply the second layer of weights, and then we apply a second nonlinearity. So this G is usually the output nonlinearity, which can be kept different so this is kept very general, but then when we actually get to the part where we study feedback alignment, we will keep everything as a linear network. So we can forget about this sigma and this G, but this is just a general setting. And we're considering a loss function where y star is going to be the true label, and then y is the predicted label. And clearly, this is the forward pass when we want to do some inference. And then when we want to do learning, we have to do the backward pass. And we want to optimize these weights, W1 and W2. And then usually the machine learning 101 that you study in school is let's do gradient descent with constant step slide. And the way to calculate the update rules is via backprop. And this is just the set of update rules. Here I'm using the notation that the delta, so this delta over here means, so delta W2 is just the partial derivative of the loss with respect to W2. So that's the notation that we're using. And over here we can see that for the updates of the pre-activation, we have the update of the pre-activation at the second layer, so almost at the output, is just the error, which if we consider a regression task, this error is really just y minus y star. And then we have this Adamar product with G prime over 2, and then the update of the second affine activation, the pre-activation, has this expression. And then if you look at it, we have this W2 transpose. So this is the main issue in backprop. This is something that has been already discussed years ago, and these are some issues that arise when we look at these updates rules. So the updates rules are what they say non-local, because basically all the neurons at the inner layer are sort of knowledgeable of what happens in the forward neurons. They know all the weights that happens in the forward pass. And this is something that is called the weight transpose problem. So you see that this goes back to the 80s. And it has been known that this is not biologically plausible. Then the other issue with this update rule is that you cannot parallelize the procedure, but we're not gonna focus so much on fixing this problem because also for feedback alignment, you cannot really parallelize the procedure too much. But the main idea is that how do you fix the fact that we are doing machine learning, so we want to sort of mimic the human brain. That's usually the ultimate goal, doing this AGI sort of stuff. And then on the other hand, we're doing backprop, and backprop is really just chain rule, but it's not observed in practice. It's not observed in the human brain. And so one of the attempts to fix this weight transport problem is really to treat backprop as a separate player. So to optimize our architecture in a different way, like having a different perspective. And so about 5 years ago, Lillikrap and collaborators published this paper that I didn't write the title, but it's basically called Random Feedback Weights, where they sort of try to propose a new algorithms that start to be more biologically plausible, or it was at least inspired by the neuroscience side of AI, where they suggested that, okay, so this is again the update weight that is sort of like the culprit that is not working so well from the neuroscience point of view. And it is that why do we need to inject these forward weights into the backprop update rule? Why instead don't we just replace it with some fixed matrix M? And this is the new update rule over here. And it's a fixed matrix that we don't change during the algorithm, during the learning process. It's kept fixed throughout the learning phase. And so why does this make sense? So what were the insight of proposing this new update rule, which is it's written over here, where the idea is that so each neuron receives some sort of random projection of the error. So this delta A2 basically represents the error, although it still comes from the previous update of delta A2. And then we multiply by this matrix M, which we can assume it to be full rank. It makes sense so that we don't fall within some kernel subspace, some null subspace, and so on. Yes. Okay, all is good. And so basically, this multiplication just means that we're injecting some random projection for the update of A1 of the inner layer. And Lillikrap also described that, argued that any matrix M is good. So we don't have to be, there were not so many prescriptions about how to choose this M, as long as there was this inner product. That's basically the angle between the error that would be used in the backprop algorithm, the sort of random projection that we have here with the feedback matrix. As long as the angle between these two errors, let's call it, is bigger than 0. So basically they're not orthogonal. So I'm not going in completely the opposite direction of where the backprop would push myself. Then it's still okay. I still learn and I still get the job done. And these are just some quick experiments that are taken from Lillikrap's paper, where they show that, so here you can see the green line, that is the backprop. This is the test error. So it does perform well. So the test error really goes to 0, and it actually looks like is doing better than backprop. Like feedback alignment, sorry, feedback alignment is doing better than backprop. And then there is this shallow here that I think is related to the random feature model, so where they just train the last layer, which doesn't look like it's doing so well. Same thing over here. This is when you have deeper networks. So this one was a shallow model. This is when you have 3 or 4 layers, and still backprop, it's doing fine. This is the pink line. Okay, so this is sort of the general idea of feedback alignment. Here I have a few slides about like a generalization of feedback alignment, which is called direct feedback alignment, where basically, which was introduced in the same year by Knocklund. And the idea is really just, let's push it further. Let's push further this idea that you wanna transmit the error signal during the learning phase via a different backward path. So instead of, again, let me change the slide. So basically, instead of transmit the error via some signal, this delta AJ, which depends on the forward path, it's the same issue as this W2 transpose that we didn't want. So let's just forget about this delta 2 and let's just inject the error directly. And so, yeah, so we use a directly connected feedback path from the error directly to the inner layers. So just to show you, so this is the update rule that we have. This is for the feedback alignment. We have M1 and M2, which are the feedback matrices. So we don't have W3 transpose, W2 transpose over here. And for the direct feedback alignment, okay, sorry. Okay, I am having, it's not moving. Oops. Okay, sorry. For the direct feedback alignment, that's the difference. So you inject the error directly here. You forget about this update for the second layer. And this is just a little sketch of how it works. This is again taken from Knocklund's paper. There are also some experiments when it shows that it behaves really well. And then, so this is all from 5 years ago, right? And then clearly there were more experiments, there were more numerical insight. They were all analyzed in these papers, and I'm sure I forgot some people, so I apologize if I forgot other people who worked on this feedback alignment and direct feedback alignment, but they actually show that feedback alignment works well, except, so there is this very strange thing that it doesn't perform very well for CNN, for convolutional neural networks, and that's still not completely understood, but if you just take neural networks, it works well, and actually there are these like very, very recent papers where the authors analyze some very complex architectures like transformers and graph neural networks, and it still performed really well. Like it almost reached the state of the art, as far as I remember. So like I was very impressed by the outcome. Okay, but then here's where I come, and I'm a mathematician, and so I'm always wondering like, okay, but I really want some theorems. That's what I'm missing, and there were definitely some preliminary theoretical results in the original paper by Lillikrap and by Knocklund under some strong assumptions. So that's let's acknowledge that. And then also more recently, there was a paper by Refinetti, and I think Ruben was also part of the paper, where they analyzed direct feedback alignment, and they did they managed to provide more theoretical results by deriving some system of differential equations for the direct feedback alignment. Also, I would like to point out that direct feedback alignment for 2-layer is equivalent of the feedback alignment. So that's why I mentioned both the feedback alignment and direct feedback alignment. So for shallow neural network, it's the same. And then when you get to deeper neural network, of course, you have some difference. And so already in this paper, it was very nice to see that there were some differential equations that can be explicitly analyzed. And then by analyzing these differential equations that draw the dynamics, it was already possible to identify 2 phases of learning, where one is alignment, where the second layer aligns with the feedback alignment matrix, and then memorization. So once it has aligned long enough so that the deeper layer finally is learned, then the second layer can now memorize and it can improve its it can improve the whole performance. And also very, very interesting is the generously breaking effect, that at the end of training, basically the second layer and the solution that gets picked by the feedback alignment dynamics, it aligns with the feedback alignment matrix that has been chosen. And this is also something that we saw in our results. So indeed, like the solution aligns with the choice of the feedback alignment matrix, or constant in our case that we chose. So there is some certain solution selection that it's very interesting, and that's going to be one of our future things that we want to work on. So how do we choose a good feedback alignment matrix to find some solution with some desirable properties? Okay, so let me just get to the convergence analysis results that we have. And how much time do I have? Because I see that it's like 6:17 over there.
I mean, you have more or less 15 minutes. 15
minutes? Okay, thank you.
Yeah, but like if it's 20, we are okay with that. Don't worry.
No, but 15 minutes. No, it should be good. Thank you. Okay, so this is our setup. So it's gonna be a lot of formula, but I'm gonna just try to walk through it. So here's what we have. We have a linear neural network. So clearly we would love to have a non-linear neural network. That's gonna be the next step. But for now, we start with linear just to get some insight and to have a tractable model. So this is what we have: linear neural network, 2 layers. So first weights, first layer of weights, second layer of weights. And we're assuming that X and Y belongs to some distribution. So here we keep it very general. For the sake of our talk, I'm just gonna assume that X is normal 0, 1, and then the Y's. So the label depends on X, basically according to this matrix over here, sigma XY, some sort of covariance matrix. But in general, even if you have like a finite data set, then you have an empirical distribution, and you can still do exactly the same calculations that we did here. The only difference is that if you have an empirical distribution, you don't have really the average, you have the empirical risk, but it's the same idea. So we're considering again a regression task. So we consider just a mean square error, and then we derive some continuous dynamic feedback alignment. So for now, the time is not discrete; it's just a continuous parameter, and these are the ODEs that we want to analyze. And you can already see here that if we pick M, this is our feedback alignment matrix. If we pick M to be full rank, you can already see that in this setting, the only solutions is indeed the minimum. So the only solution is indeed what we want to find, is indeed when W1 times W2 is equal to this covariance matrix. There are no other spurious stationary points. So that's already something nice from the feedback alignment. And so let's try to analyze this ODE. So what we do, the idea is that we want to do some sort of smart change of variable to make the ODE simpler, to make it analyzable. So we resort to the singular value decomposition of the covariance matrix, where lambda is just diagonal, and then we have 2 unitary matrices U and B. And then we decompose the weight matrix W1, W2, and the feedback alignment matrix in a similar way. So this W1 tilde, W2 tilde is what remains after we sort of conjugate with these matrices. We keep it generally just a general orthogonal matrix, arbitrary. So in this setting, what can we do? So this is diagonal, and now W1 and W2, we are initializing them to be diagonal as well. So it seems like we're putting a lot of constraints, but it turns out that it still mimics, this whole construction still mimics the dynamics when you have a full matrix, even though if we're starting with very specific initial conditions where everything is diagonal. But so if all these matrices are diagonal, what happens is that the system of ODEs decouples. So you get that the system of ODEs remains diagonal for the whole duration of the training. And it gets even better because, just to show you, so basically here is just an example where you have 5 equations over here and 5 equations over here. You have 10, but actually they are not all coupled between each other. They're just pairwise coupled. So the first line over here is paired with the first line over here. The second line is paired with the second line, and so on. So everything really decouples in a super nice way and super simple way. And now we can use the full force of different calculus 1, calculus 2, and analyze it and actually solve this differential equation. And this is our first result. So we have this system of differential equations. So now they are scalar now. Now it's a scalar. So theta 1 and theta 2 are functions. They're not matrices, they're not vectors. This D is the feedback alignment constant that's in the diagonal of the feedback alignment matrix. And this lambda is one of the singular values of our covariance matrix. So the first theorem is that if we pick this specific initialization, then the product theta 1 times theta 2 converges to the true signal, converges to the singular value. And it converges, what is nice is that it converges in a monotonic fashion. It can be either increasing or decreasing depending on your choice of initial condition. but it converges exponentially fast. And you can see also that if lambda is big, so the bigger the lambda, the fastest the convergence. And this is just some little numerical simulation that you can see. This is theta 1, the behavior theta 1, behavior theta 2, behavior of the product. Okay, so just a little bit of comments. So why do we choose this initialization, which is really weird? So you see that the second layer is initialized based on the choice of the first layer and based on the choice of the feedback alignment constant. So the layers are not IID initialized. So this turns out that in this way, that first of all, the analysis is simpler, but also at some point we're going to see that when we're talking about this implicit regularization, this actually is a good initialization because it helps learning the signals, learning the singular values in an incremental way. So starting from the largest singular value and then decreasingly learning them incrementally towards the smallest singular value. And then the other comment that I have is what I told you, that you have some exponential convergence, and the largest is the lambda, the fastest is the convergence, which again sort of tells us this idea that maybe you're going to learn first the largest components, first the principal components of the models, and then in a decreasing way you learn the secondary components, which is usually what people want, right? You don't want to learn the smallest components, which are usually tied to noise, so that they don't give us any insight or information about the model or the data. Okay, so but then here's the question: do we really need this strange initialization? Well, not so much. Oh yeah, that's the last remark before talking about that, is that in this solution selection. So you can see that the solution is going to look like that. So theta 1 is going to be some function, which is as a very ugly expression. So I didn't write it here. And theta 2 is just theta 1 squared divided by 2d. And this is the alignment that you get. I know that it might look like, oh, we cheated because that's our initial condition. It turns out that you have some sort of d-dependence of the second layer also if you take any different initialization. So that's where you have the alignment, that the second layer aligns with the feedback alignment constant that you choose. This is just some stupid graph, some little sketch. This is the parabola. This is the parabola of solutions of theta 1 times theta 2 equal lambda. And you see that depending on d, they all converge to a different point. Now the question is, which one is probably the nicest? The minimum L2 solution. We still don't know about that. We're working on that, but we already noticed that there is a different choice. There is a different selection of the solution that we can exploit that for applications possibly. Okay, so this is the second thing I wanted to say, is that, okay, do we really need a special initialization? Actually, no, we can take theta 1 and theta 2 to be initialized randomly and independently. You still get convergence, but you lose something, and you lose the fact that you have a monotonic convergence. So here you can see these wobbles over here. So the convergence is not monotonic anymore. So if you want to do feedback alignment and then do early stopping, maybe you stop somewhere over here thinking, oh, okay, I'm already reaching a good level of accuracy. But no, if we're going to push your training dynamics a little bit further, then you will get even closer to the signal. So if you take any initialization, you might get tricked if you do early stopping. That's one thing. And then again, you see this selection solution over here. So the solution, again, depends on the feedback alignment constant, because you have indeed this alignment thing that is very typical of feedback alignment algorithm. Okay, everything generalizes to deep network. This is just a quick slide where you do exactly the same singular value smart change of variables, so that the dynamic decouples, the dynamic becomes scalar, and then you have this system of differential equations, which again, it can be easily analyzed. It's really simple. This notation over here, it just means that it's the product theta 1 times theta 2 times theta 3 all the way up to theta L minus 1. So it looks complicated, but it's doable. And then you reapply the same machinery. The idea is that if you have this specific initialization, so again, first layer initialize at random, second layer you sort of initialize, second layer and up, you sort of initialize it as a power of the first layer. Then in this case, the analysis is simple, and then you get monotonic convergence. But again, the convergence results without the monotonicity also holds if you initialize all the layers independently. So we still manage to get convergence guarantees in the continuous setting and also in the discrete setting that we will get at the end where we will probably just blast through it to stay within the time. And so, but let me focus on this implicit regularization. So we know that now the system converges, but how does the solution look like? So what is implicit regularization is this idea that during the training, you're learning all of the parameters or the features of the model in an incremental way. And this property has been already been noticed, it's been already been studied for the gradient descent in these two papers. One was by Gauthier and collaborators in 2019, and another one was by Daniel Gissin, I think he's French, another collaborator in 2019 as well, where they were basically studying gradient descent initialized at with initialization very close to zero. We know that zero for gradient descent doesn't work, but if it's very close to zero, then it takes very long time to actually escape these stationary points, which is a local maximum. But then with this spatial initialization, it is possible to actually prove that to see also numerically that all the singular values are learned incrementally. So you start with a bigger singular value, you learn in it, and all the other singular values are still not learned, and they start to be learned just after the previous singular values is learned. So you really see some sort of like a step function where one singular value is learned sequentially after the other. And this was the like the mathematical formula where you actually prove that the product of this theta 1 and theta 2, their analysis was also in the singular value setting, by the way, for linear neural network. And you see that this product over here, it converges to a theta function, to a step function, sorry, where the step function tells me that when the time, so when the learning is before a certain threshold time, capital T, you have zero. So you haven't learned a thing. But then after a certain threshold, you automatically learn the singular value. And the threshold here is really given by 1 over the singular value itself. So then you can see that if the singular values, suppose you have two singular values, lambda 2, if lambda 1 is bigger, the time at which you learn lambda 1 is going to be smaller. So you learn it sooner, and then the second time, 2 is going to be bigger and you learn it later. So you learn lambda 2 later. So that's when you have really a sequential learning. And this is what was called in those papers, implicit regularization. So the idea was that we want to sort of study the same phenomenon also applies for feedback alignment. And this is what we found. Oh yeah, so this is just to show you that you can really see these increments, like really a bunch of steps where the features are incrementally learned. So the orange line is when you have just one layer neural network, so a perceptron, pretty much. And in that case, implicit regularization does not happen. But when you have 2 layers or even more layers, you really do see this step function. And the idea was that, okay, can we do the same with feedback alignment? And this is what we found. So this is just an informal statement of the theorem. For feedback alignment, it does depend on the initialization that you pick. So there are certain initializations where you learn your components, or supposing that lambda 1 is always the biggest one, and then decreasing. For some initialization, you have this incremental learning. So you first learn the biggest components and then it decreases. For other initialization, you learn it the other way around, which is really not what you want. But it does happen. It doesn't happen with high probability, right? So with high probability, we are lucky. We get into the nice setting and we are most likely going to get regularization. But for other settings that are kind of, it's with small probability, possibly with measure 0 probability, but it might happen that you learn it backwards. And that's definitely what people do not want. And this is just an example where you see that the blue line is the one corresponding to the smallest eigenvalue, singular value, lambda equals 0.5, and is the one that jumps up to 1 as the first one. And then the one that jumps up to 1 as the last one is lambda equal 2. So it's the largest eigenvalue. So this is one of the settings where it might happen. But this is all numerical simulation that is like carefully crafted so that you can see anti-regularization. We haven't seen anti-regularization in like an actual experiment on a real data set. We haven't seen that yet. This is just theoretically, it may happen. So that's our message. And this is some more extra details where, again, we basically prove that there is some rescaling. You see this delta, that's the one that we sent to infinity, some rescaling of the initial condition and rescaling of the time such that you actually see this separation and these stepwise functions that appear. And the time is an increasing, this threshold time is an increasing function of lambda for this specific initialization. What happens is that this implicit initialization, anti-implicit regularization usually happens when you do not choose the special initial condition that we were prescribing, right? We had this specific initial condition, initial initialization scheme that it looked like it was super artificial, but at least in that sense, in that setting, we do not get this sort of behavior. So this is actually the next slide. So if we stick to this initialization scheme, we get some sort of regularization. So this, you can see that this green line over here is the first one that it gets learned, and this corresponds to, I apologize, the picture is a bit small, corresponds to the largest eigenvalue, lambda equal 100. While the blue line is the last one that is learned, it corresponds to lambda equal 10, which is the smallest eigenvalue in this case. So what was really interesting is really to see how different initialization can give you really different outcomes. That was really surprising. And let me just quickly finish. So this is also the discrete dynamic. I'm just gonna show you very quickly the proof. The proof is that, okay, we're considering feedback alignment with constant step size. So here is our step size eta, and this is the standard discretization. So if you take W1T over here, it's basically the Euler forward discretization technique, the standard one. And here we're proposing some sort of midpoint rule that helps us with our analysis. And it also has, it also came to us, like the intuition was also from the fact that if we keep our special initialization where the second layer depends on the first layer, then also the update of the second layer, it makes sense that it may depend on the update of the first layer as well at time t+1. This was some sort of intuition that we had, and that actually helped with the analysis. But so in both of these discretization strategies, we get convergence. This is the general results. We get linear convergence as long as eta, the step size, is small enough. And by small enough, I can tell you, like, I have formulae for how small eta needs to be. I just don't want to write them here because they're very ugly. I think I have them in some extra slides if you want to look at them. But it is that, yes, we get linear convergence for eta small enough, which is actually nice. This is in the 2-layer case. We have an analogous result for the deeper, like deep network case in the midpoint rule, in the midpoint discretization strategy. It can be also generalized for the forward, for the normal Euler discretization method, but then it gets super messy to prove it. But we can do it. And so let me just get to the end. This is just some little experiment. We just wanted to compare a little bit feedback alignment and gradient descent. This is one of the next questions that we want to tackle. Like, okay, is feedback alignment great? It converges, amazing, biologically plausible, but can we actually establish some comparison between feedback alignment and gradient descent? And this is just some little experiment that we did with linear encoders, but definitely there is more to do. Definitely there is a lot more to study. And so let me just quickly finish with just like some wrap up, saying that feedback alignment has good potential, and well, based on papers on experiments, it scales to deep architectures, and it reaches very good performances, and it is biologically inspired. So I'm sure people will be very interested in that, and indeed, like the audience over here is very interested in feedback alignment. But from my perspective, we really need to study more these algorithms. So first of all, what about stationary points? So we see that for the linear case, we only have minima. We don't have spurious stationary points, unlike gradient descent. But then what happens in the nonlinear network? Then we need to do a little bit more. Our intuition is that feedback alignment is going to sort of wash away some of the spurious stationary points, so that will help the convergence to the actual minima that we want to reach. And also the next idea that we have is that there should be some hierarchy of convergence between layers. So probably the bottom layers gets learned first, and then the second layer, and so on. So there is a different speed of convergence of the learning. And I think there was some analysis already done in the paper by Ruben and Maria and other people, that they were also analyzing that, if I remember correctly. And then again, what is the comparison between feedback alignment and gradient descent? Is there some game formulation? I know that like nowadays game is like the hot topic, and maybe feedback alignment can have a game formulation. to analyze better how the dynamic evolves. And then finally, how can we fine tune? How can we choose our feedback alignment matrix to actually select a good solution that is helpful for our applications? And then I stop over here because I think I went over time. I really apologize, but thank you for listening.
Thank you, Manuela, for the talk. It was really interesting. And yeah, you went a bit over time, but that's not a big deal.
Sorry about that.
So it's time for the questions. Are there any questions from the audience?
Yeah, I have a question, a very simple one. What's your take when you look at nonlinear networks? You seem to be talking about the hierarchy of convergence. What's the insight, or what is making you think that it might actually happen that way? What I'm saying is, introducing the nonlinearities would essentially introduce a nonlinearity in this type of approach that you have. In this type of ordinary differential equation. What is the concept that we see in those ODEs that would look like something where we have nonlinearities and for which we know that there is something that is being dampened or something else? Is there any insight from ODEs and nonlinear ODEs that would apply to this?
Yeah, so our idea is that, so for in the linear case, clearly this singular value decomposition setting does not happen. Like, we cannot use this method for when we have a nonlinear network. But when we look at the linear network for like deep linear network, we notice that the solution at its layer behaves like a power of the first layer. And so that was our idea, that then there is like a different rate of convergence, because you know, when you're very far from the minimum, then maybe the first layer converges faster. And then when you're very close to the minimum, the other layers follows, because then you have a power that drags the error to zero. So that's our idea. But definitely, so you can say that if you have a nonlinear network, if you linearize the ODE near the equilibrium point, then it behaves like a linear network. It behaves like a linear ODE, then the dynamics should look similar. So you can do some perturbative analysis. That's one thing that we're thinking about. But then clearly what happens if you're very far from the minima, then you cannot do any perturbative analysis, and then that needs some different tools that we are thinking about. It's
one of the things that I keep on pushing my my team to look into, but they keep on telling me that it's I'm an old-fashioned type of person. It seems to me that there is I would like to see somehow at some point in time, people look at the behavior of not just the eigenvalues, but also the eigenvectors that are part of this dynamics. Mm-hmm. It would seem to me that there are a lot of richness that comes out of these dynamics that is not encompassed only in looking at the eigenvalues. What's your take on this? Do you have any views on this?
No, I agree that looking at eigenvalues, it's a bit limiting, and eigenvectors definitely help a lot. So the only thing that I thought so far, it's sort of using some random matrix tools. We haven't done any, we haven't started at all on this in this direction. But my idea is that, so the feedback alignment matrix is a fixed matrix, but it's you can think of it as a random matrix. So what happens like on average case? So my idea was to sort of study some average case, do some average case analysis on the feedback alignment matrix, and then studying the evolution of those eigenvectors and so on. But that's very up in the air. I haven't really had time to sit down and look at it yet properly.
Okay, thank you.
Thank you. And Ruben has raised his hand.
Hello, thank you for the presentation. To bounce back on what Igor said and what you said about the power law and the eigenvalue, it makes me think about the work of Charles Martins and Mahoney that analyze the eigenvalue of the weights during training. Mm-hmm. So maybe your theoretical analysis could be joined to this type of work. But yeah, I had a
you mean
question.
the five phases of learning? Sorry for
Yes,
you mean that paper,
yes.
right? Yeah.
Yeah, exactly. And so the question was like, so in our paper we have the align and memorize, and we show that in the memorize phase, we go to the minimum of the loss landscape that has the same symmetries as the random matrix or the matrix M. So how in your analysis, in your eigenvalue analysis, would you see this symmetry? If you incorporate this symmetry analysis, maybe you could show, in theory, this align and memorize process in your with your analysis. You see what I mean?
Yeah. So yeah, I think I see what you mean. I think in our case with this singular value decomposition, we sort of lose this symmetry, right? Because we decouple every single entry of the matrix, while you analyze the matrix as a whole. And then I think you do this like cosine similarity, so you're really calculating the angles between these two matrices. And for us, everything would be scalar, so it's it could feel a bit like diminishing, but I think so. Let me just show you the solution of the second layer. It looks something like this, right? Like, can you see this? Again, my pen does. Okay. So this is our alignment result.
Okay. But in some sense, you show the alignment just in other space. I mean, you just do the SVD. So in some sense, you show that there is alignment.
Yeah. We show that there is alignment, but the symmetry there is not really a symmetry here, right? It's really just the solution that gets.
But maybe my point was like to incorporate the symmetry in the original space into this SVD space.
Okay. Yeah. That's interesting. Yeah. That's a nice idea.
I think if you are in the eigenvalue space, then everything is, as you say, you have a set of differential equation. And I think because the goal, I think in the end will be to show that this is a constraint optimization where you have to align with the weight and with the matrix and to align with the teacher weight, for instance.
Right.
So maybe in this simpler space that you have, because you are in the eigenvalue space, then it's simpler to formulate this program. So
yeah,
that's
a good idea. Yeah, that's a good idea. Yeah, we didn't really consider a student-teacher setup. We just implicitly said that Y depends on X in this form, right? So we kept Y general, but it makes sense. Like maybe we enforce a little bit some teacher setting and then see what happens. Yeah.
And a last clarification. So the difference between your work and Lily Crabb work, the first one on feedback alignment, the first part of your work, is that because you are in the eigenvalue space and you can compute some convergence rates towards the eigenvalue, right? Which Lily Crabb did not show when he showed alignment in linear network.
Yeah, correct. And he also proved that the continuous dynamic converges when you start at zero. So with zero initialization. For us, it's a little bit more general. So we proved that for any initialization, you have convergence.
Yes. Okay, perfect. Okay, thank you very much.
Thank you.
Thanks to both of you. Are there any other questions? Okay.
Yeah, just kind of a comment, and I hate to be that person saying those things. To come back a little bit to what Ruben was saying, it would seem to me that this eigenvector thing comes about because eventually what you get to see in those nonlinear systems eventually is potentially that the basis, the eigenvector basis, is not as, let's say, is becoming a little bit collinear or close to collinear somehow. And there may be some dynamics that are coming there that are essentially not accounted for by just having a linear analysis on the linear network. So anyway, I'm just mentioning that as an item to think about, maybe.
Yeah, thanks. Some food for thought. No, for sure. Thank you.
Good. Any other question or comment at this point? Okay, I think we can close here. I want to thank you again, Manuela, for the presentation and for replying to our questions. It was
thank you very much.
Really nice having you. And as usual, we'll put the video on our YouTube channel. I'll send you the link by email when it's up.
Okay, thanks.